time we stopped here. We were talking about how adding multiple pulses is a good thing from a harmonic elimination perspective. Uh, the objective is, do we want to see if we can eliminate harmonics as well as maintain a large RMS value, right? That's what we would like to see, versus keep losing RMS value whenever we try to eliminate harmonics, right? So we think that this may be possible by adding these multiple pulses. So and that's what people have been working on in power electronics. So adding multiple pulses is one way to go forward. Another way is, of course, to build more complex converters. So we talked about the half bridge. So multi-level inverters is another way that people are proposing to go forward with our objective, which is to eliminate harmonics and maintain a large RMS value. So how does this new converter achieve that? So this converter basically, what it does is allow us to, at the output here, see either 0 VDC, minus VDC, or 2 VDC, or minus 2 VDC. I mean, it's basically two single phase, it's basically two H bridges that we saw before. The H bridge can give us what? We can get from the H bridge what? If these two switches are on, we can get VDC. If these two switches are on, minus VDC. If these two or these two are on, we get 0 at the terminals of the single H bridge, right? So this is 0 VDC minus VDC. This is 0 VDC minus VDC. So if we time it properly, we should be able to get 0 VDC minus VDC and 2 VDC and minus 2 VDC, right? So if this is VDC, this is VDC, we'll get 2 VDC at the output here. And similarly, we can get minus 2 VDC, right? So that's one way. So if I'm able to get more sort of intermediate levels, so I have the 0, I have an intermediate level, I have a higher level, which is basically utilizing the full DC link. So I have two DC sources. One thing to note here is that this is made, you need independent DC sources for this topology. So these are independent DC sources. So if they're being fed from an AC source, you will need to have a transformer for each of those, a secondary of the transformer connected to each of these half bridge, full bridge converters. Okay, so they have to be isolated DC sources here. So sounds nice, right? Before, with the full bridge converter, we said that we had the single pulse, and then we added some zeros, and we were able to improve the waveform quality a little bit, yeah. And now with multiple pulses for the single phase converter or the single H bridge converter, we said we were able to improve the quality a bit more, yeah. So now we were able to add even more stages, more voltage levels. So the idea is, with more voltage levels, we should be closer to a sine wave and hence have better harmonic content or lower harmonic content, yeah, in our output voltage, yeah. And that's what we can get with a converter like this. So we would operate, for example, V1 or the first H bridge to produce this waveform, second H bridge to produce this waveform, and hence the output will be the sum of the two. Okay, and then of course the tool that we will use to assess if this waveform is good or not is Fourier series, right? For all the converters, we have to, after we look at come up with the waveform, we have to look at what the Fourier series output of the output voltage waveform looks like, so we can assess if we are closer to achieving our objective of maximizing RMS value and eliminating low order harmonic content. This is the main objective. So what they did was they came up with the Fourier series for the output voltage that we have here. Again, you don't have to derive it. It will be these equations you have. So this would be the Fourier series for the output voltage. And this is the peak value of the nth harmonic voltage, right? So our objective is to what? Is to make sure that we maintain this V1 as large as possible, right? We want to maintain V1 as large as possible. And we want to see if we have variables that we can play with. And here we do have some variables, because we have the width of these pulses is something we can play with, right? So if we play with the width of these pulses like we played with the width of that single pulse that we had before, we will alter the harmonic content. And that's what we see here, right? The nth harmonic voltage is dependent on, fine, 4 VDC over n pi, you cannot play with that, but you can play with these alphas. If you play with these alphas, then you can probably alter the nth harmonic voltage harmonic. So can we find a way to independently eliminate harmonics and increase the fundamental. That's what we would like to see. So we came up with the textbook introduces a definition. The definition will be something that will help us see or assess the value of the fundamental harmonic, it's a fundamental voltage. So it's called modulation index. This modulation index is basically how much fundamental do you have from this waveform that you are creating at the output of the converter, right? So it's a ratio between the fundamental voltage that you have, V1, the first harmonic or the fundamental harmonic, and the value of the peak value of the square wave, peak value of the square wave, peak value of the square wave. So V1 is the value of the fundamental harmonic, and then the Fourier series for the square waveform is what? 4 VDC over pi, right? 4 VDC over pi. So that's the 4 VDC over pi, and then here I have 4 VDC over pi if the value of the DC voltage here in the Fourier series, if you have a Fourier series with a peak value of VDC, if this has a peak value of VDC, the Fourier series has a peak value, the nth harmonic of the Fourier series has a peak value of 4 VDC over pi, correct? But if this is 2 VDC, then this will be 2 times 4 VDC over pi. Okay, so it's because I've changed the DC voltage, assuming I did that here. And in this converter, I do that because I'm using 2 DC sources, right? So I have 2 DC sources that I'm using to create the output voltage waveform. So if I would like to compare what I get from this waveform versus the capability of my DC source, capability of my DC source is 2 VDC, right? So the capability of my DC source is 2 VDC. So if I create a square wave using a 2 VDC input source, I will get a peak value for the fundamental equal to 2 times 4 VDC over pi, right? So that's sort of my comparison, base for comparison. What is this circuit giving me? I get that from my Fourier series for that specific circuit, right? So for the fundamental harmonic from this circuit will give me, V1 is equal to 4 VDC over pi, and I have to put whatever angles I'm getting. I have to divide that by my reference. My reference is, what can my source do? My source is a 2 VDC source that can create a 2 times 4 VDC over pi fundamental for a corresponding square wave created from that source. So they call that the modulation index. It's just you have to find the reference, something to compare to. So if you have a multi-level inverter now with 4 sources, you have a 4 VDC source, not a single VDC source. So what you're going to compare with now in that case would be 4 times 4 VDC over pi. That would be a reference because that's your DC source. You're going to take your fundamental that's going to be created from that specific topology and divide it by your reference to come up with a ratio for what you call a modulation index. The modulation index is how good you've utilized your DC source to create a fundamental voltage the fundamental voltage that you need. Okay? So we will do that for several converters. So this is modulation index for this specific topology that we saw, and this 2 is because we have two DC sources. So now we have 2 interesting equations. This equation and this equation. This equation is the equation for the nth harmonic. And this equation is the equation for the modulation index. This equation has variables n alpha 1 and alpha 2. This equation only has alpha 1 and alpha 2. So maybe, remember in the single pulse converter, when we eliminated the third harmonic, we were also affecting the magnitude of the fundamental, right? We were decreasing the magnitude of the fundamental when we added some zeros. When we added some zero, the areas with 0, we changed the value of the fundamental voltage. Yeah. So we would like to see if we can make that eliminate harmonics in this case without affecting the fundamental. So if I'm able to solve these 2 equations, eliminate the third, fifth, seventh, eliminate the harmonics by satisfying this equation, without affecting the modulation index, then I've done that, right? So that's what they say here. So we can eliminate the harmonic M can be eliminated while maintaining modulation index Mi if you solve the equation. So this equation, this is what we get from here, from this equation. So if I would like to eliminate, V3, for example, or V5, I would like to solve the cosine M. M in this case would be 5. 5 alpha 1 plus cosine 5 alpha 2 equals 0, while maintaining this modulation index, right? So I would like to make this part 0 for the fifth harmonic, or for the mth harmonic. At the same time, I would like to satisfy this 2mi. For example, I want to maintain modulation index to be 0.7. Can I make this 2 times 0.7 equal to cosine alpha 1 cosine alpha 2, as well as solve this equation while making it 0? If I'm able to do that, then I can eliminate harmonics without detrimentally affecting my fundamental voltage output out of the converter, which is what we want to do. Always we want to do that. We want to have a certain DC link voltage, and that DC link voltage we want to create a certain fundamental voltage. That fundamental voltage we want to have it as close to a sine as possible, so eliminate as much as harmonic as possible. So that's this in this converter topology, these equations will guide that. So these are nonlinear equations you have to solve iteratively. That's we will not discuss that. We will not solve it here in class, but this is the basic theory behind what we're doing here. If we solve these and able to find the solution that satisfies these equations while maintaining the modulation index, then we have achieved our objective. Maximize fundamental, eliminate harmonics, right? Then they go on and say, okay, if I was able to do that if I was able to come up with equations to do that for the while we have two converters in series. So this would be called a 3-level converter. Why is it called a 3-level converter? Because the output is either 2 VDC, VDC, or 0. It has, you can see 3 levels in the output of the converter. Again, if you look at, the multi-level converters, you can call them, again, you can look at the output waveform and say here, this is 1, 2, 3, 4, 5 level of the output. But we typically call this, I'll show you the one that, for example, this one, we will call this a 3-level converter. It's not called a 5-level converter. I don't know. Why is it called? I'm not sure why it would be called. I would say it's called a 3-level converter because it's looking at, in a certain polarity, it sees 3 levels. So the idea is, okay, I was able to create with these two series converters a certain number of levels. Fine, you can. It has a 5-level output, but it's called 3-level, right? No, but for do we call it 5-level converter? We call it we call it a 3-level converter. It has a 5-level output, regardless of the name, guys. Regardless of the name. Yes, sure. That's why we call it 3-level converter, because I agree. So I'll show you the difference between the phase voltage waveform and the line voltage waveform. So the phase voltage waveforms will have a certain number of levels. The line voltage will have a certain number. So we call it based on the line voltage. So line voltage will have 3 levels. The phase voltage will have 5 levels, regardless of the name. Regardless of the name, guys. Okay. The phase voltage here. This is the phase voltage. So this is a single phase. The phase voltage will have these 5 levels. So it has a 5-level output, and we'll see why the line has less than that. We will show you the waveforms, but we will go. The idea is we have here 2 of these converters in series, and we came up with a set of equations based on the Fourier series and the modulation index that allows us to maintain a certain modulation index and eliminate harmonics at the same time. So solutions to these equations will be the proper alphas that we can choose to satisfy our goal. And we can do that with more converters in series per phase, right? So you can add more converters in series per phase and do that. The nice thing about this topology is you can build a high voltage converter, but what is the voltage stress on each of these switches? Exactly, right? Because one is on, one is off, right? So if one is on, one is off, then the one that's off will see VDC across it. So you can build a 10,000 volt converter using a 1,000 volt switch by using maybe 10 of those in series, for example, right? So that, and this is done, practically this is done. And for example, RasGas has trains 6 and 7, the new trains, new RasGas trains, meaning it's a, compressor, the natural gas compressor that they use, they call that a train, yeah. So they have a motor drive running, motor drive and a big motor running a compressor. So they call that assembly a LNG train, yeah. So the drives used for the LNG trains in trains 6 and 7 in RasGas are based on this topology. Okay, the older trains, they are based on thyristor converters. So it's a thyristor inverter, thyristor-based three-phase inverter, like we've studied before. The inverter operation for thyristors. So it's based on that topology. Because they were older trains, IGBT technology was not really common at that time. This topology was not very commercial maybe when they started, but now, I mean, the trains 6 and 7, the newer trains, they are based on this kind of topology. How many of these H bridges they have, I don't know, honestly. But they have a ton of these. They would have many of those in series to create one phase. Right? And then after you create one phase, put a second phase, put a third phase. Each of these phases, phase shift them with respect to each other by 120 degrees, and you've got your output voltage. You've simulated a three-phase supply. Okay. So add more of these in series. What happens, of course, is your output will have more of these levels, right? More of these levels means more angle choices, right? So all these angles, how much zero that you have every half cycle is a variable that you can play with. So the next thing we will see is they will come up with a Fourier series for the waveform. From the Fourier series from the waveform, they will extract the fundamental, right? From the fundamental, this is an equation, right? The other equation is the equation for modulation index. We said the modulation index is how much fundamental I have, right, compared to how much DC source I have. So V1, which is the fundamental voltage, divided by 4 times K times VDC over pi. K is the number of these blocks in series, right? So if you have 2 of them in series, it's 4 times 2 like we did for the previous example there. In this case, they just generalized, right? So, and now it's the same thing. Solving this K times Mi equals all of these angles equation, and these summation of these cosines equals 0 equation. If you solve these for the mth harmonic, you should be able to eliminate the mth harmonic without affecting the value of the fundamental voltage, right? So that's the idea. It's the same idea that we talked about before. Okay, if you look at this waveform, this switch is obviously on for the most amount of time, right? And this switch is on for the least amount of time, right? All these converters are in series, right? All these converters are in series, right? Does it matter if I make this the small voltage and this the big voltage? If I make this switch on for the output voltage here on for a short period of time, output voltage in the last one on for the large period of time. At the end of the day, I'm adding all of them in series, and that's creating my stepped sine wave, right? So what they're going to talk about, what we talk about next in the slide is, I can sort of flip those around. Why would I do that? If this is on for a long period of time all the time, and this is on for the short period of time all the time, how much current is this conducting versus how much current is this conducting? Yeah, so V1 will be conducting a lot of the current, a lot of current all the time, and hence losses will be more in, for example, this converter. So sometimes you want to equalize the losses, because when you're building one of these large systems, again, you cannot make something very hot and the other stuff, not as hot, right? I mean, you want to design a cooling system, and you want to use the same switches all over, and you want to make sure that the lifetime of the switches is the same, right? So you would distribute this, for example. So what we will show next is, here they sort of flip them around. Look, in one half cycle, this is the smallest, larger, the largest. The second positive half cycle, they flipped, they moved them around. This is, the smallest, they moved them around to equalize the heat, basically. It does not really affect the output, right? The output does not change. So the Fourier series and their modulation index, etc. The theory is still valid, except that from a design perspective, you want to do that because you want to be able to control your heat distribution in the system and make sure that the life is equal across the system. Yeah, because again, electronics and capacitors and inductors, again, all of these components, the more you heat them, the less lifetime. So you want to distribute the heat evenly across the system. Yeah. So one way to do this, again, one way to build these converters would be one way to build this nicer waveform, right? This is a nicer waveform than our single pulse or single pulse with zeros. Looks like a nicer waveform. The best thing we could do with a single H bridge, or even in three-phase configuration, is either the single pulse or single pulse with zeros, or multiple pulses, which is nice, and we will extend on the multiple pulses section now, discussion again. But that's the limit of that single output, single two-switch configuration or two-level output type converter, right? If you want to improve on that, you have to go to more complex topologies to give us a nicer stepped waveform, stepped sine wave that we have here. We can improve this even more, right? If we now, instead of just having these steps, within these steps, we add multiple pulses, right? So not just a stepped waveform like that, but within these steps, I can add multiple pulses as well and see how it can improve. Like we did for that simple single H bridge, we can do the same for the multi-level inverters as well, right? But before we do that, there's another. So one type of multi-level converter can be built from these cascaded. It's called the cascaded H-bridge converter. This is called the cascaded H-bridge converter because it's made of a series cascade of these H-bridges that we discussed. Another way to create this is what it's called the diode clamped multi-level inverter. The benefit here, the advantage here, is that we don't need independent sources. For the H bridges, you needed independent DC sources for each of the H bridge. So if you were feeding this from an AC system, you would have an AC system with you would have to put a transformer. And that transformer would have to have many secondaries. All of these secondaries would have to be isolated, and then each isolated secondary would have to rectify its output and create a separate DC source for each of these cascaded H bridges. And you would have to do that for all the phases, right? So it's a bit of a pain. So there's a lot of secondaries in a converter like that, right? So it's used. It's a practical. You practically use it. Rasgas has them. Train 6 and 7. Siemens, Robicon. Siemens bought Robicon, and Robicon used to, develop these drives, and they're commercially available. And the nice thing is they are, you can use lower voltage switches, very low voltage switches, if you put many of these cascaded H bridges in series. The other type of topology that you can create these multiple levels with is there are two other types called the diode clamped and capacitor clamped. We will not discuss this in too much detail. I just want you to know the name and the topology, the benefits and advantages and disadvantages. Advantages of this versus the cascaded H-bridge topology is the fact that here you can use a single DC source. You don't need many DC sources. Of course, you can also cascade these if you want more levels. So what does this buy you? This buys us, if I have, let's look at one phase only, not two phases. If I look at one phase only, right? If I turn on these two switches, what do I get between these two nodes? If I turn on S3 and S4, what do I get between this positive node and the reference? 0, right? If I turn on these two switches, I get 0, right? How about if I turn on the two top switches? Two top switches I measure here. I get VDC between this point and ground. How about if I turn on the two middle switches and turn off the output switches on the outside? What do I get here versus ground? Assuming there's current flowing. Assuming there's current flowing, meaning these diodes are conducting current. So these diodes are conducting current. If these diodes are conducting current, it means that this point is connected to this point, and this point is connected to this point, and these two switches are on. So this is a short circuit here. So what does this mean? It means that I'm at the output here. I'm connecting this output to the middle point of these two capacitors. Right? So what's the voltage at the middle point of two capacitors across a DC source? VDC over 2. So I can get 0, I can get VDC, and I can get VDC over 2 at this node here. Yes? If these two are on, it's a short circuit, right? It's a short circuit, and I'm saying that we have continuous current. Okay, that's the condition. Current is flowing. If current is flowing, that means current is coming out here or going in here. If it's coming out here, how is it? It's flowing from here through this diode, through this switch, and here. If it's going back here, it's going here through this switch, through this diode, and back here. Right? So current it's an AC voltage, right? So we're creating an AC voltage here. So current will be coming out or coming in, and if then the one of the diodes will be conducting current, and there will be a short circuit. So I'm connecting the output to VDC over 2. So I get the same nice 5 levels in the phase voltage that I have: VDC, half VDC, 0, minus half, and minus VDC. Okay, so I get the 5-level phase voltage output. Okay. So, any questions on this? So theoretically, I can create this nice same stepped waveform that I had, but with this. I can create something like this, right? 0 VDC over 2, VDC, VDC over 2, blah, blah, blah. I can create this type of waveform. And I can, again, next thing we'll talk about is I can add more pulses in here if I want to add more finer control. Like this is giving me something, some value for RMS voltage, fundamental RMS voltage. What if I want to reduce that a little bit, or increase that a little bit, or reduce the ripple content of current? Then the best thing to do is add more pulses within here. If I add more pulses within here, then I can control the ripple content. Right? Because here, here, if I have an RL load, I have a fixed voltage RL load. What's going to happen? Current will ramp up. Fixed voltage RL load. What happens? Current will ramp up. Right? So I don't have control over ripple current anymore. Right? But if I add more pulses now within this same switching period, then what can I do? If I find the ripple current increases, I can bring it down to 0. Turn off the switches. Bring down the current a little bit. Then bring it back up again, bring it down, bring it back up again, and control my ripple content. Right? So that's where we're heading. Right? That's where this is all heading. So here they talk about how this converter operates, the three cases that we talked about, and here what is the voltage stress across the switches. So take this loop, for example. Here, for example, take this loop here. This outer loop here. These two switches are on. The two switches that are off, assuming that you have, again, there's more details to this, balancing circuits that balance the output, the voltage across the two switches, etc., etc. But for our purpose, let's assume that we have switches that with proper balancing circuits across them that would balance voltage across two switches in series. Okay, if that's the case, then I have two switches in series that are seeing what voltage? VDC. So each switch will see VDC over 2. Right? So switch stress here is less than the full bridge H. If I compare this to the H bridge converter, the switches would see, each switch would see the full voltage, full DC voltage. Here, each switch will see half the DC voltage. Right? So this switch sees half the DC voltage. Right here, this loop here, the diode is on, for example. The diode is on. This is a short circuit. This switch sees the capacitor voltage only. Right? This switch sees the capacitor voltage only. So there's an advantage here. It also buys us the advantage of switch voltage stress being reduced. I don't have full voltage stress, full DC link voltage stress across each switch. That's one of the advantages of multi-level inverters. Versus an H-bridge. So versus an H-bridge, the H-bridge, the switch will see the full DC link voltage. Here it sees half the DC link voltage for this topology. If I add more of these in series, so this would be called a 3-level multi-level inverter. You can add more switches in series, and you would have more capacitors in series and more diodes in series, and create more levels at the output. You can do that. I don't think we show that here. Oh, actually, we do. Okay. So here, this is another version of the diode clamp multi-level inverters, but instead of 4 switches in series, I have 6 switches in series. And here I've divided up my DC link voltage into VDC 0, VDC over 3, 2 VDC over 3, and then VDC. Right? So I can theoretically get 0, 1/3, 2/3, and VDC. And same on the negative side. Okay? I can do that for one phase, I can do that for the second phase. Okay. Yes? No, this is a very nice topology actually. There's not a big disadvantage. One of the limitations of this one, not disadvantage, one of the limitations or something you have to pay attention to is, for example, you have to make sure that these capacitors are actually maintaining the voltage at VDC over 3, 1/3 VDC. Because let's go to the simpler one here. What did we say is happen when these two, if I turn on these two switches, if current is coming out, right? What's happening? Current is flowing in this out through this diode to the output. Where is it coming from? From the middle point, right? So what is it doing? This is a point between two capacitors. So it's going to be taking current out of this capacitor network. So what does that do? Exactly, it will discharge some capacitor. This current that's coming out will discharge the capacitors. So you have to make, and what did we say happens when the current is coming back into the system? It goes back here and can charge the capacitors, right? So you have to make sure that you maintain the voltage across the capacitors to be balanced. I mean, you have to balance the capacitors. So balancing capacitors is one thing that people did a lot of research about, right? Because it's not obvious. I mean, it's remember, you have this switch network and you're building this circuit. Is it perfectly balanced? Do you have the exact same resistance and losses in the path of current for this phase and for this switch and this switch? Not necessarily, right? Are these switches identical 100%? Is the voltage drop across the switches 100% identical in all the switches? No, there's variation, right? So because of the variations in your circuit topology, your wiring, your capacitors, your inductors, your voltage, your drop across the diodes, the temperature distribution in the system, all of these things cause deviations. The dead time that you choose, all of these things cause deviations in the circuit. So what happens is if you leave it as it is and you don't balance, don't pay attention to the balancing, what will happen is you may end up discharging one capacitor completely and fully charging this one to the VDC voltage. So if you do that, do you have a multi-level inverter? No, because this is down to 0. And when you're connecting these two switches, it's connecting down to 0, like as if you're doing these two switches on at the same as well. So it's useless, right? So balancing capacitors is a big deal here. So people spend years working on modulation techniques that can balance this. Actually, two ways to do it: modulation techniques or hardware balancing. So some people what they did was they put DC to DC converters across something like a DC to DC converter across each of these capacitors. And they would always, I would make sure that the capacitor voltage, and these DC converters maybe are fed from the source. So they would make sure that you're always maintaining the capacitor voltage here to VDC over 2 in this case. So there's hardware balancing and then there's software balancing techniques. So many papers on those. Okay? The advantage of software balancing is no extra losses, no extra components, etc., etc. The advantage of hardware balancing is fine. It's always going to happen, right? So there's no glitch in the software. So people did this and people did that. So So that's one of the things that you have to pay attention to when you design one of these. Yeah. But it's a very this is I would say the workhorse of you know motor drive industry, higher power motor drive industry. So, and they would use, for example, they would also use this in a cascaded fashion. So you would see some converters that instead of using just an H bridge in cascade like what we have here, because this H bridge would produce what? 0 VDC over 2 and 0 VDC over 2 and VDC, right? Each of these H bridges. But if I have this H bridge, inside this H bridge I have a multi-level inverter. Then I have 0, 1/3, 2/3, and I have more levels basically, right? So sorry, this would be if it's just a pure H bridge, it would be 0 and VDC, right? 0 and VDC and minus VDC, right? 0 VDC minus VDC. If inside this H bridge I have an H bridge multi-level inverter, then I have 0 VDC over 2 VDC minus VDC over 2 and minus VDC. So I have more levels within that block as well. Yeah. So you can do that. There are people that I think Toshiba has converters that are like that. Yeah. Again, advantage is you're closer to a sine wave. Everybody wants to go closer to a sine wave, right? And the nice thing about this, this type of switching is you're close to a sine wave without a high switching frequency, right? I achieved my objective of becoming closer to a sine wave, but I don't have lots of switching. If you want to improve even further, you want to improve the harmonic content of your current even further, you either have to keep adding more levels, which is expensive, or fine, at some point you say, okay, now it's become too expensive. Let me try to pulse width modulate within one of these levels. I add more pulses within this level and see if I get some benefit. You will get some benefit for sure, right? So you have to, it's a advantages and disadvantages. It's a cost versus benefit sort of thing. You cannot keep adding more levels to infinity, because again, the reliability of a system depends on everything operating properly, right? So if you have a system that has many components, then it's prone to problems. Right? Even though one of the advantages of using this type of topology is the fact that if this fails, I can just put a short circuit here, and I can still get an output voltage. Right? This is one of the nice things about the cascaded H-bridge topology. I cannot do that with a multi-level diode clamped inverter by itself here. Right? So again, it's some advantages, some disadvantages. But all of these are helping us do what? Achieve being closer to a sine wave, meaning removing some harmonic content, removing more harmonic content, at the same time maintaining a high value of fundamental RMS voltage. Right? So there's another kind called the capacitor clamp. We don't have pictures of it here. Instead of these diodes here, for example, instead of these diodes here, I would disconnect this and I put a capacitor here across these two switches. And this capacitor here is called a flying capacitor because it's flying. There's not even it's not reference to the ground, or it's not reference to the top here. It's just flying. It's connected here in the air across these two switches. If I'm able to control my converter such that I maintain half the voltage across this capacitor all the time, right? Charging and discharging this capacitor half the voltage all the time, then across these two switches I have a capacitor. So anytime one of these is open, one of these is closed, it will have the other one that's open will have a voltage across it equal to VDC over 2, right? So this will be VDC over 2. Then, so if this is VDC over 2 across these two switches, then, and this is all VDC. So what's left across the top and bottom switches? VDC over 2 as well, right? So that's another way to, okay, I'm going to clamp my voltage across each pair of switches to VDC over 2, right? So it's called the flying capacitor converter. You can look up the topology, but the idea is the same. I'm able to get the same sort of number of levels at the output from this converter topology. Okay, now we want to add more pulses. We saw that we can add, 3 pulses and solve a number of equations, right? But people said, okay, I cannot keep doing that. I would like to add a lot more pulses and see what because again, the more pulses I add, the more angles I have to play with, the more freedom I have to eliminate harmonics and not affect my fundamental voltage, right? So people worked on many modulation techniques to do that. So we have what is called pulse width modulation, and you've seen that in your class project, right? In the modulation, in the pulse width modulation, the way it operates is I compare a triangular waveform with a reference sine wave. I know you did not get to that in your project, and but I hope you did it in simulation at least, yeah, right? Yes, no?
10-4.
10-4 what?
Yes, we did.
Okay. So the way it operates, I have a triangular waveform, which is a high frequency carrier waveform. Right? This is my high frequency carrier waveform. This triangular waveform is the frequency of this waveform is a switching frequency, right? And then I have my modulating waveform, which is this sine wave that I would like to create at my output, right? This is my reference duty cycle, basically, right? So you remember what we said, you know, this, what we have, each of these phases that we're creating, you know, whether it's 2-level, 3-level, whatever it is, it's equivalent to this, you know, pole here or pole here moving between these two nodes, right? And this is plus VDC and this is 0, right? So if this is down here, I get 0 at the output. If it's up here, I get VDC, right? And if I keep switching this fast enough, and it's fast enough, and I maintain a certain duty ratio, so I have a high switching frequency, and I maintain a certain duty ratio. So I switch at 50 kilohertz with a 50% duty cycle. So what do I get at the output here? Assuming my duty ratio is D. What do I get at the output? Average value. Exactly, VDC times D, right? Whether you do that for, if this D is fixed, you get a fixed output. If this D is a sine wave, what do you get? No. If this D is a sine wave. No. If this D is a fixed value, you get a fixed value. If D is 0.5, D is 0.5, you get 0.5 times VDC here. That's what you get. After filtering, okay? Forget about I'm filtering. Remember, I'm talking about I have either for DC converter I have a filter, or for a motor application I have a motor winding, so it's a filtered wave, right? So I get 0.5 times VDC, but it's a fixed value. But what if I make this D vary sinusoidally? What do I get? A sinusoidal output. But this sinusoidal output, it's going to vary between what and what? D equals, what's the minimum value for D? Can it be minus? Can it be negative? It cannot be. So it's between 0 and 1. So the output here is going to be between 0 and VDC. So I need to create a sign. I need to create a sign that's offset by, at the maximum, if I want to create the maximum sine wave that I can get, I will create a sine, and the offset will be 0.5 times VDC. If I want to create here VDC and here 0. But I can keep the offset 0.5 and create what? This, right? I can do this. Right? And if I have two of these, so this is one. I have one here, I have another one here. I have another one here, right? If I have another one here, can I create the same thing or not? I can create the same waveform exactly, right? If I create the same waveform exactly, what do I get between the two converters? What do I get at the output voltage? No. Think. The output voltage here between them is this voltage minus this voltage. If I put a load here, the load voltage would be this node's voltage minus this node's voltage. So what is the voltage across the load? Come on, they're identical. I'm saying they're identical. So if they're identical, what's the voltage across the load? 0. I have 5 volts and 5 volts. The difference is 0, right? And that's why if we have uh, a full bridge converter, I need to phase shift these with respect to each other. In a full bridge converter, I phase shift them 180 degrees. So I create this, I create this, create this. Okay. So now I want to subtract them. So this minus this. This is like, let's say this is 1. Oh, this is 1. 1. 1. Minus 1.
0.
Exactly. Right? How about this? No. This is 1
Minus 0.
minus 0 is 1. Right? And now here,
So you're
0. That's not triangular. I just, because I took 3 points, it looks like it's a sine wave. I mean, this is sinusoidal, this is sinusoidal. How about here? Right? So I will get this nice sine wave. Right? And it's because I phase shifted this output with respect to this output by 180 degrees. Right? So in 3-phase, how will that work? You want to emulate the 3-phase sources that we have. Remember the 3-phase sources, that we have? If they were what? If they were equal to each other in magnitude, but they were phase shifted by 120 degrees apart, the loads here, the current at the loads, the load currents are all equal as well. They would sum here to 0 because all the currents are equal in magnitude and 120 degrees apart, because all the voltage sources are equal in magnitude and 120 degrees apart, so we can use our single phase equivalent circuit. So we do the same. We create a voltage here that is, again, offset by half VDC and a sine wave. We create a voltage here that is offset by half VDC as well, but phase shifted with respect to this by 120 degrees. Right? What's going to happen to the line voltage now between these two nodes? What will the line voltage look like? The line voltage will be the subtraction of the two. What's going to happen to the DC offset? The DC offset minus the same DC offset is going to go away. Anytime you have the same, I mean, again, if the line voltage, if the phase voltages have values that are the same, you subtract them from each other, they will go away they will disappear from the line voltage, right? So that's why we can create these DC offset sine waves, and the line voltage will be a nice sine wave. I'm not going to draw the line. It will be a nice sine wave with no DC offset, basically, right? And the same thing you will do here. So you phase shift this one with respect to this one by 120 degrees. This one with respect to this one by 120 degrees. And you will get this same effect that we want to create using these 3-phase AC sources. Okay? So how do you do all of that in a nice way with multiple pulses? You have this triangular waveform, and you compare your triangular waveform. So the way we built it in the lab, I believe, is you will have a triangular waveform on one end, and you have your modulating signal on one end. Remember, this modulating signal is an offset. This is your duty ratio reference between 0 and 1. You can create a sine wave as small as you want or as large as you want, as long as you offset it by half VDC. Offset it by half VDC. If you offset all the three-phase waveforms by half VDC, then the offsets will disappear because they will be subtracted from each other. And what you'll be left will be the difference between the sine waves at the output, right? So it's basically a DC to DC converter with variable duty ratio, right? Basically, that's what it is. It's like a buck converter with variable duty ratio. But you put three of them together, right? And the duty ratio, you control it to be a sine wave, and you shift the duty ratio with respect to each other. That's basically what it is, right? That's why the basic buck boost and buck boost converters are really important, because based on these topologies, your understanding of these topologies will help you understand any other topologies in power electronics. Yeah. Anyway, so the way you would do it is fine. You would either this would be positive or this would be negative, or vice versa. And anytime the positive input is greater than the triangular waveform, you get a pulse. You get a change in the level of the output. Yeah. Anytime it's less, it goes down. Anytime it's more, it goes up. Anytime it's less, it goes down. Right. So, and if you control and then take this now, take this, the outputs from this would be what? Anytime the sine wave is greater than the triangular wave, you get a high signal. Anytime anytime the sine wave is here and the sine wave is greater than the triangular, you get a high signal. Anytime it's less, like here, you get a negative signal, right? So you can control you can take these signals, and you can control your converter, your full bridge converter, to operate such that you are only producing complementary switching. So this and this are always complementary, or this and this are always complementary. If you do that, do you get any zero states? Right? If 1 and 2 are on, and then 3 and 4 are on, either this or that, you don't get any of the zero states, right? And if you operate, so you take these pulses and operate in this fashion, right? You take these pulses and operate the converter such that you never use the states where 1 and 3 are on and 4 and 2 are on. You always get an output voltage that is between minus VDC and VDC, right? And this has a width that is proportional to the length of time, or the amount of time the sine wave is higher than the triangular wave, or vice versa, right? So we've produced a pulse width modulated signal that is modulated sinusoidally. The modulating signal is a sinusoidal signal. The high frequency signal is a triangular signal. Whether it's you can make this triangular signal look like this, or you can make the triangular signal look like this, or you can make a triangular signal look like this. At the end of the day, is the pulse width going to be, again, your modulating signal is a sine wave. Your modulating signal is a sine wave. So the intersections here will still be proportional to the modulating signal anyways, right? Whether you do this or that and intersect the sinusoidal signal, the difference between them will be some harmonic content. Okay? At the end of the day, it will be some harmonic content differences, and that's what people, okay, no, this is better than that, we publish a paper. This is better than that, we publish a paper. That kind of thing. Okay, let's mix it in the multi-level converter, use this and that, and then publish a paper, right? So all of this, I mean, research is good. I mean, people have to. Wayne is laughing, but this is what, at the end of the day, it's the output. Okay, intersect with the triangular carrier, you'll get something proportional to sine wave. Okay, you want to improve the harmonic content a little bit and publish a paper, it's fine, which is good for you. You can develop a differentiating product for yourself and stuff like that with IP, and no problem, right? But I'm saying let's not stress on, I mean, you will see sometimes like this, sometimes like this, sometimes like this. The idea is the same. High frequency carrier and a modulating signal, right? So obviously, if I put more of these high frequency carriers within a certain half period, then I get more intersections. If I get more intersections, then I get finer control of my output voltage, right? And that's where they come up with something called the frequency modulation index. It's the relationship between, basically, is how many of those triangular waveforms you're able to put in there and compare to your sine wave. It's a metric, figure of merit, right? If you can put more of those, you can have a finer system. The other figure of merit is what? So the one figure of merit is the quality of the waveform. It will depend on the frequency modulation index. The other figure of merit is not figure of merit. Other control controlled parameter that you have is your so one is the frequency modulation index and one is the amplitude modulation index. The amplitude modulation index depends is what controls the magnitude of your RMS output voltage. So if you have triangular waveform like this, I can intersect it to the sine wave down here, or I can intersect it to the sine wave down here, right? This will obviously produce a higher fundamental. To produce a higher fundamental, because for example, let's say anytime the sine wave is greater than my triangular wave, I have a pulse at the output. So now my pulse here has a bigger duration than this pulse, right? So bigger pulse duration means I have more RMS output voltage, right? There's more area under the curve, right? So I have more RMS output. So if you want to, so if you increase your duty ratio of your peak value of the sine wave, for example, means your duty ratio is continuously across the board more higher for this sine wave than this sine wave, then you've obviously increased your amplitude modulation index, right? So that's the other control parameter that we'll talk about briefly. Again, we don't have too much time anyway. So this is called bipolar switching. You switch between positive and negative only, and I've not utilizing the states where the two top switches, two bottom switches are producing zero. Is this good enough or not? If I add zeros, will it help me? It's more. Why not? It's more control, right? Anytime you have more control, it may help, right? Anytime you have more control, it may help, because a sine wave does not go between zero maximum value and minimum value, right? The sine wave rises slowly, so it would make sense to maybe, why not utilize the zero output states of the converter, and that's called unipolar. And again, the bipolar switching we talked about 1 and 3 and 1 and 2 and then 3 and 4, and they describe that here. Whenever the sine wave is greater than a triangle, turn 1 and 2 on. Sine wave less than triangle, turn 3 and 4 on. Okay, that's we'll not spend too much time on that. For unipolar switching, what they mean by unipolar switching is that within a half period, I'm not going to the negative voltage. So I'm utilizing the converter's zero states. If I utilize the converter's zero states, does this look closer to a sine wave or does this look closer to a sine wave? The second one looks closer to a sine wave. So you would expect that the harmonic content of unipolar switching. So in bipolar switching, I had only one carrier that I was comparing my triangular waveform against. In unipolar switching, because I have one carrier, and these are switching at the same time. These are switching at the same time, so I don't need two carriers to compare my output with. Here I have two carriers. I need this will be operating with one carrier. This leg would be operating with one carrier. This leg would be operating with another modulating signal. That's 180 degrees phase shift. Take those two, compare it. And now you're running them independently. They're not, 1 and 2 are not running together, right? Each one is being controlled by one of the outputs, and they describe that here, right? The result of that is a better, closer to a sine wave type waveform. Yeah. So I will stop here. I think we've covered. This is the frequency modulation and amplitude modulation equation that we talked about. Again, if we increase the amplitude modulation, we increase the fundamental output, right? We said that if you increase the ratio of the peak of the sine wave to the peak of the triangle, make them closer, then you get a higher RMS value, and that's what this equation said. So, and the frequency modulation is the frequency of your triangular waveform over your sine wave. How much of these triangular waveforms do you have within a sine wave period, right? That's a figure of merit. And then the amplitude modulation is the magnitude of your sine reference waveform, the duty ratio reference, to the triangular peak value, the maximum value of the sine versus the maximum value of the triangular waveform, right? The closer they are together, the higher the modulation index, right? If the maximum value of the sine wave is 1 and the maximum value of the triangular wave is 1, then your modulation index is 1. That's the highest value of output you can generate, and hence you get an MA is 1 and V1 is equal to VDC in that case. Okay, so we'll stop here. I hope you learned something. And again, the next thing they will do is look at the harmonic content. And we obviously said that the harmonic content of the bipolar switching will be better. I will just show you that table that shows that. So this is the table for bipolar, and this is the table for unipolar. For bipolar, I get fundamental output. I get harmonics at the switching frequency, double switching frequency, 3 times switching frequency, 4 times, etc., etc. This is where I'm oscillating between VDC and minus VDC all the time without using the zero states. If I utilize the zero states of the converter, my lowest order harmonic is now double the switching frequency. So I've eliminated more harmonics that way, right? My closest harmonics is at twice my switching frequency. So obviously it's a better harmonic content. We'll stop here. I hope you learned something about power electronics and enjoyed it. So